March 27th, 1980. 6:30 in the evening. The North Sea. A worker on the Alexander L. Kielland platform hears a sound that should not be possible inside a steel structure. A single crack, sharp as a gunshot. And then the entire rig tilts 30 degrees in under 20 minutes. Within 5 minutes, the platform capsizes completely. 123 men die in freezing water. The cause? A single weld, 6 millimeters thick, cracked, invisible to every inspector who had ever looked at it. I'm Joe. Welcome to By Design. Subscribe if you like knowing what most people don't. You'll want to be here for this one. The Alexander L. Kielland was not some marginal operation held together with shortcuts and optimism. It was a semi-submersible platform built in 1976 by a French shipyard, certified by Det Norske Veritas, one of the most respected classification societies in the world. 5 enormous steel columns rose from submerged pontoons and supported a pentagonal deck the size of a football field. Accommodation blocks, mess halls, recreation rooms, a helipad, everything required to keep over 200 workers alive and functional in one of the most hostile marine environments on the planet. And the North Sea in winter does not negotiate. Waves regularly exceed 50 feet. Winds run at hurricane force. Water temperature sits just above freezing, which gives an unprotected person somewhere around 15 minutes before hypothermia takes over. Platforms operating in those conditions aren't built to adequate standards. They're built to survive. The Alexander L. Kielland had been built to survive. It had the certifications to prove it. But those certifications covered what the rig was when it left the shipyard. What happened to it afterward? That was a different story. The Kielland was originally designed as a drilling rig. In 1978, Phillips Petroleum needed additional accommodation space for workers servicing the nearby Edda production platform, so they converted it. And conversion means modifications. Modifications mean welding new equipment onto an existing, certified structure. One of those additions was a hydrophone, a sonar device used to communicate with subsea equipment. Not a large piece of kit, around 15 feet long, a few thousand pounds. To mount it, a small bracket was welded onto one of the rig's structural braces, a massive steel tube designated the D6 brace, part of the framework holding one of the 5 legs in position. Just a small flange, unremarkable, functional. It was also never submitted to Det Norske Veritas for review, never assessed for its effect on load distribution through the brace, never welded to the specifications that applied to primary structural connections, and never inspected using the non-destructive testing that critical welds required. It was a minor modification, so it was treated like one. You know that feeling when you're watching a film and the disaster is already obvious to everyone except the people inside it? That's this. The bracket goes on in 1978. The rig goes back to work. 200 men eat on it, sleep on it, play cards on it, write letters home from it. And inside the D6 brace, something very small and very patient begins. This is the part worth really understanding, because this is where the horror actually lives. When metal is welded, the heat from the process creates a zone around the joint where the steel's internal structure changes. That zone cools differently from the surrounding material, and that difference creates internal stresses, microscopic imperfections, sometimes tiny voids and inclusions that you simply cannot see. Under static load, most welds handle that just fine. But the North Sea doesn't apply static load. It applies cyclic load. Waves, constantly, in every direction, hundreds of times a day, thousands of times a month. Every time a wave moved through the structure, the D6 brace flexed, and that bracket transferred load into the brace at a point it was never designed to receive load, which meant the weld at that point experienced a tiny additional stress every single time. What happens next has a name: fatigue crack propagation. And here's the problem. The crack doesn't announce itself. The structure doesn't sag, it doesn't groan. It doesn't give you any warning you can see or hear. It just accumulates damage, quietly, invisibly, cycle by cycle, until what's left simply can't hold anymore. The crack in the D6 weld likely began almost immediately after the bracket was installed. Every wave worked it a fraction further, through 1978, through 1979, into 1980. By March of that year, the crack had spread through almost the entire cross-section of the weld. At that point, the bracket was being held in place by almost nothing. And then the weather turned. On March 27th, the North Sea was running 20 to 30-foot waves, with winds gusting past 40 knots. Standard conditions for that time of year. Exactly the kind of conditions the platform was designed to handle. At 6:30 in the evening, the fatigue crack finished its work. The weld failed. The hydrophone bracket tore away, and in doing so, it ripped through the structural tube it had been mounted to, fracturing the main brace itself. And that brace wasn't decorative. It was a primary load-bearing member holding one of the 5 legs stable. The moment it failed, the load it had been carrying redistributed instantly to the adjacent bracings. Those bracings were never designed to absorb that kind of load. Not dynamically, not in rough seas, not with the platform already in motion. A second brace failed within seconds, then a third. The entire D-leg column began to collapse, and the platform tilted 30 degrees in the time it takes to make a cup of coffee. 212 men were inside when it happened. Furniture slid, equipment fell, people were thrown across compartments. And then, darkness, because the electrical systems failed almost immediately. Emergency lighting didn't come on. Lifeboats, designed to be deployed in relatively stable conditions, became nearly impossible to launch at a 30-degree angle in heavy seas. 5 minutes after that first fracture, the Alexander L. Kielland rolled completely upside down. The accommodation modules went underwater. Rescue vessels from the nearby Edda platform were close. But in freezing water, in darkness, in breaking seas, the window for survival is measured in minutes. 89 men survived. 123 did not. Norway's worst offshore disaster, caused by a weld the size of your finger, on a bracket weighing a few thousand pounds, attached to a structure designed to survive the worst conditions in the North Sea. And the investigation that followed left nowhere to hide. The Norwegian government commission recovered the wreckage, and the evidence was unambiguous. They found the failed D6 brace. They found the fatigue crack pattern consistent with years of cyclic loading. They found the bracket that had altered the load path through the brace without any analysis of what that change would do. And they found that Det Norske Veritas had never been notified of the modification. The organization that certified the structure had no record that the structure had been changed. The conclusion was blunt. This disaster was entirely preventable. Not bad luck, not weather, not some unforeseeable combination of events. A modification that bypassed review. A weld that bypassed inspection. And the word minor applied to something that was structurally anything but. And here's the part that should really stay with you. The welder who made that joint almost certainly followed the procedure he was given. The defects found in the weld pointed to inadequate specification, not sloppy execution. The engineer who approved the modification probably saw it as routine. The inspector who didn't apply non-destructive testing likely believed the documentation justified that decision. Nobody in that chain set out to cause a disaster. They were professionals, operating inside a system that had not yet learned to treat a modification on a certified structure as a potential redesign of that structure. The system failed, and the system's failure had a body count. Which leads to the obvious question. Did the industry actually learn anything from this? Or did it just hold a memorial and move on? The offshore industry after the Alexander L. Kielland did not look like the industry before it. And that matters, because these changes aren't abstract rules. They are direct translations of how those men died into systems designed to make sure nobody dies that way again. Every structural weld on an offshore platform now requires documented certification, inspection, and non-destructive testing. Not most welds, every weld classified as structural. The distinction between a minor modification and a structural change is no longer left to judgment on site. It's defined by regulation. If you weld anything onto a primary structural member, it triggers formal review, no matter how small it looks. A bracket like the one on the D6 brace would now be treated as a major structural intervention, because that's exactly what it turned out to be. Fatigue analysis also became standard. Engineers now model cyclic loading and crack propagation for structural members exposed to repeated stress. They don't just ask, is this strong enough? They ask, how many cycles before this fails? And non-destructive testing, ultrasonic, radiographic, magnetic particle, became mandatory at installation, because that moment, right after a weld is made, is the only time a hidden defect can realistically be caught before it starts doing damage. After that, the steel closes around it, and the crack is alone, in the dark, with nothing but time and waves. The rules changed. Human nature didn't. The pressure to label something minor, to move faster, to trust paperwork over physical verification, that pressure is still there. It didn't disappear. It just became harder to act on without leaving a trace. And somewhere, in safety offices across offshore platforms today, versions of this story are still used in training. Not as history, as a warning. Because minor is not a category, it's a question. There's a memorial in Stavanger, Norway. A simple structure, 123 names. The Alexander L. Kielland didn't sink because the North Sea was brutal that night. The North Sea is always brutal. It sank because a bracket was attached to a structural member without structural review, welded without structural specification, and left without structural inspection. 3 failures, each one considered acceptable at the time, by a system that didn't yet understand what acceptable meant in that environment. 123 men went to work on a certified, modern, professionally operated platform and did not come home. Because somewhere in a process everyone believed was working, a 6mm weld was left alone in the dark to do what fatigue cracks always do. That weld didn't fail the day it was made. It failed the day the North Sea finally asked it a question it was never designed to answer. And by then, there was nothing left to inspect.